Hello, the basic principles of quantum mechanics can be explained without employing so-called complex numbers and functions of complex variables. However, complex numbers are traditionally used in quantum physics in the very first formulas of this science, and therefore it is important to understand, at least on a general level, what complex numbers mean and how they are used. For our next stories, we need to know the simplest information from the theory of complex variables. The imaginary unit I is just the square root of minus 1. A complex number z is a pair of numbers x and iy recorded as their sum. The conjugate number z star is x minus iy. The square modulus is z star z. We will use Euler's formula for complex exponent. In this video, I will talk about all that stuff in more detail. We will also derive a formula for the sum of several sine cosine functions with close arguments. The simplest quadratic equation x squared equals 1 can be rewritten as x times x equals 1. The equation has two solutions, x equals 1 and minus 1, which can be verified by direct substitution. If we now consider the more general equation x squared equals a with no negative a, then its two solutions can be written as x equals plus minus the square root of a. Note that the square root of the positive constant a itself is always positive and the root of 0 is 0. In another example, equation x squared is 4, the square root of 4 is 2, and two solutions to x are plus minus 2. Now let's study the equation y squared equals minus 1. By analogy with the previous equation, we write its formal solution in the form y equals plus minus the square root of minus 1. The square root of minus 1 is called imaginary unit and is usually denoted by a small letter I or j. By definition, I squared is equal to minus 1. Note that all people feel strong cognitive conflict when they hear about the imaginary unit for the first time. What does the root of minus 1 mean? We never meet similar objects in real life. When counting the objects around us, we use natural integers 1 to 3 and so on. Using the subtraction operation, we arrive at the concepts of negative integers and 0. By dividing integers by each other, we come to the concept of rational numbers. By performing geometrical calculations, we are led to the concept of irrational numbers such as the square root of 2 or pi. For example, the square root of 2 is the length of the hypotenuse in a triangle with equal legs of length 1 unit, and 2 pi r is the perimeter of a circle of radius r, also called the circumference. But all the numbers just mentioned above are real numbers. They appear as a result of calculations of quantities, measurements, or arithmetic, algebraic, or geometric operations familiar from school and suitable for use in everyday life. The square root of minus 1 is the next level of abstraction. This is the simplest imaginary number. Complex numbers contain both real and imaginary parts and stay at the next level. Let's consider the equation y squared is minus b with positive b. Then its two solutions can be written as y is plus minus I square root of b. Here plus minus I square root of b defines imaginary numbers in general form. Their squares are minus b. But there is a problem here. The fact is that all of this stuff, both the imaginary unit and the imaginary numbers in general, and their generalization in the form of complex numbers, are never ever used in practical calculations in everyday life. But then why are these numbers needed at all? The father of one of my friends had a higher academic education in mathematics and successful work experience in the IT field for 30 years, and one day he admitted, "I have never used an imaginary unit in my work in my entire life. I don't understand why imaginary numbers are needed at all. Explain this to me in simple language or give me a simple example, when we can't operate without them." We will answer these requests a bit later in this video, but for now we will continue our presentation. In general case, a complex number z is represented by a pair of a real and an imaginary number x and iy, and is usually written as their sum, x plus iy, when notated by letters, or 1 plus 3i when notated by numeric notation. Note that the imaginary unit I is placed before the letter with letter designation and after the number with numeric designation. Using these notations, we can easily add and subtract complex numbers. The real and the imaginary parts are added and subtracted separately and do not mix with each other. The imaginary unit I plays the role of a label separating imaginary components from real ones in these operations. We can also multiply complex numbers. The imaginary unit is multiplied according to the usual algebraic rules and I squared is equal to minus 1. Having defined these standard operations, we can show that solutions to quadratic equation may have both real and imaginary parts in general case. For example, we can find that equation z squared minus 2z plus 2 is 0 has two solutions, 1 plus minus I. You can check this by direct substitution as shown here. Finally, we can also divide numbers. To simplify the division result, we use here a special procedure called denominator rationalization. It works as follows. For any complex number z, we can define so-called complex conjugate number z star if formally replace I by minus I. Then the product of a number and its complex conjugate is equal to x squared plus y squared, which is always a real value. In the above division procedure, we multiply the denominator by the number that is the complex conjugate of the denominator, and to compensate, multiply the numerator by the same expression. As a result, we have a real number in the denominator. Well, this product z star z plays an important role in physics, and it is called the square modulus of the complex number. Then, by definition, absolute value or norm of z is the square root of z star z, and it is equal to the square root of squares x and y. This is somewhat reminiscent of the Pythagorean theorem and sees the idea that a complex number can be drawn as a point on a plane. We know that the point xy can be depicted on the real plane using the usual rectangular Cartesian coordinate system. In a completely similar way, we can introduce a complex plane with the coordinate system xiy and mark the complex number z on it. Distances r from points to the origin of coordinates are determined from triangles using the Pythagorean theorem. We see the same expressions in both cases. We will continue to consider only the case of the complex plane. Recording the expression for the absolute value of a complex number, we understand that this absolute value is just equal to the distance from the point to the origin on the complex plane. Next, we can introduce the so-called polar coordinate system. This means that instead of x and y coordinates, we specify the position of the point using distance r and angle phi. From the triangle, we can express rectangular coordinates in terms of polar ones. X is equal to r cosine phi and y is the same with sine. The whole complex number z is sum of cosine and sine therefore. Now is the time to introduce the famous Euler's formula e to the I phi is cosine phi plus I sine phi. It relates the exponential function of the imaginary argument to trigonometric functions. Substituting the Euler's formula into the last expression for z, we obtain the short formula z is r e to the I phi. Actually, this is the end of the information which would be better for you to know to understand basics of quantum science. Next information is just from the category nice to know. First of all, a few notes about Euler's formula. Exponential functions of the real argument are well known not only in physics but also in many other areas, for example in financial applications. For instance, stock prices very often show exponential growth over a limited period of time. Besides that, distributions of stock returns usually take the form of bell-shaped curve described by the function e to the minus x squared. The exponential function of a real variable x is a fast-changing function with the change rate equal to the value of the function itself for any value of x. You can easily check this using any online calculator as shown in the example given here. A huge number of other formulas and relations are also known for the exponential and trigonometric functions of real arguments. Surprisingly, it turns out that all these formulas continue to work correctly if you substitute complex arguments instead of real ones, provided that we take the Euler's formula into account. Note that this is not obvious, not trivial, and just amazing fact. Okay, great. Further, just for reference purposes, we wrote down the formulas expressing sine and cosine through imaginary exponents. Now we will discuss functions of complex variables. We have presented the formula z is r e to the I phi for the complex number. Quite similarly, we can introduce the complex exponential function e to the z for the complex argument z. This is also an important and commonly used formula. The function e to the z belongs to the class of so-called analytic functions. Analytic functions are functions that depend on the sum of x plus iy. Here we give examples of analytic and non-analytic functions. Analytic functions are extremely useful because they can be applied to calculate integrals using so-called residue theorem, but this story is outside of our review. Another interesting example is related to the visualization of the function e to the ikx. Here two options are possible. In the first case, we draw the cosine and sine in two mutually perpendicular planes corresponding to the real and imaginary part of e to the ikx. The wavelength lambda, that is the distance between the nearest equal values of the function, is 2 pi over k. In the second case, we draw a helical curve. Sometimes you can meet a combination of two options, but option 1 prevails in physics as the most informative. And now we come back to the question, why we need imaginary unit complex numbers and functions of complex variables. The answer is as follows. Complex numbers never appear in everyday life. As a rule, complex analysis is not needed in industrial production, civil engineering, product design, medicine, chemical industry, financial reporting, and information technologies. We use complex variables only in hard mathematical calculations in physics, financial analysis, and other applications. This allows us to shorten records and simplify some heavy calculations with sums and products of power, exponential, trigonometric, and logarithmic functions. In addition, complex functions are used in quantum mechanics by professional physicists to perform Fourier transforms, calculate integrals using so-called residues, and for special cases of calculating so-called transition amplitudes. However, all these professional tools are not really needed to understand the basics of quantum mechanics. Finally, there is no simple practical example of using complex functions. They are specially designed to fix complex problems, and therefore there are no simple obvious examples of their need. This is the answer to the question asked by the father of my friend announced in the beginning. Therefore, we'll now look at a not simple but useful example. We'll obtain a formula for the so-called wave packet, made up of several cosines with similar arguments. In the figure, you can see a graph of the sum of 21 cosines determined by numerical methods using Excel or Python tools. We need to define a simplified formula. From Euler's formula, we know that cosine can be determined as the real part of the exponential function. Obviously, this also works for the sum of cosines as we do here. After making the transformations, we get the final formula. We see that the wave packet is described by a carrier wave modulated by the envelope. The smaller the delta k, the greater the distance between the large peaks of the envelope. The larger n, the narrower the peaks. If delta k tends to 0 and n tends to infinity, only one central peak remains, and other peaks run away to infinity. In conclusion, let's consider the so-called quantum packet consisting of a sum of complex exponential functions. In the pictures you can see relevant three-dimensional images. It is described by exactly the same sum of elements as we have already discussed in the previous example. Therefore, we can use already results. Real part of psi is exactly the just reviewed function f. It contains fast oscillations modulated by the envelope. Note that now we do not look at all outlying peaks and analyze only one central peak located at the origin of coordinates. We can also calculate the square of the psi function. We see that the imaginary component is killed by the complex conjugate pair, and the relation becomes simpler. Fast oscillations go away from the absolute psi squared, and only the peak with slowly oscillating wings remains. We will use all these results in the next story. Thank you for watching.